Hello guys, nice to see you. How are you doing?
Good afternoon, we are fine.
Cool, nice. Hello, good afternoon. So, uh, last our discussion was about electrical DC electrical circuits, where we considered some battery power supply with internal resistance and external load resistance. And we figure out how to calculate electric current in such circuit, taking into consideration internal resistance, electromotive force of this battery, and also figure out at which value of load external resistance should be in respect to the internal resistance in order to achieve the highest output energy delivered to the load resistor from the battery. So in that case, this condition is satisfied when load resistor is equal to internal resistor of the battery. So today we continue with DC circuits. We will discuss connecting different resistors in series and parallel. Also, we will focus on the first and second Kirchhoff's laws, which help to analyze currents in different DC circuits. And we'll see, hopefully we have some time, we will also discuss RC DC circuit. So it will be a resistor and capacitor. And in this case, we will deal not just with constant current in direction. And so far we deal with constant steady state current, means it doesn't change neither in direction nor in time. However, if we have a capacitor and resistor, then we will have constant current in direction, but it will be changing with time. That would be interesting to discuss in more details. So let me switch our screen to the slides. So let's start with connecting resistors between each other. So let's first consider this electric circuit where we have two resistors connected in series to some battery, which provides potential difference between terminals delta V. So we have some current, resistor 1, resistor 2. And obviously there will be some voltage drop over resistor, like potential drop over resistor 1 delta V1 and over resistor 2 delta V2. So since they are connected in series, we can write the following. Electric current, like through the circuit, is equal to electric current running through resistor 1, and that is equal to electric current running through resistor 2, because there are no any branches where electric current can go. So everything is connected in series. Another thing what we should write here, that total potential difference, which is created by the battery, is kind of split between two resistors. So delta V1 plus delta V2. So now we would like to determine the magnitude of some so-called equivalent resistor, R equivalent, which will be able to substitute these two resistors R1 and R2 connected in series. So in this case, we can do the following. So delta V, so we express this delta V1 and delta V2 in terms of electric current and values for our resistors R1 and R2. So we can write for delta V1, we can write I 1 times R1 plus I2 times R2. Taking into account that I1 is equal to I2, and that is equal to I, we can take it out from parentheses. So we will have I times R1 plus R2. And in other way, if we have delta V, the same potential difference here in this equivalent circuit, delta V can be represented as the same current, because resistance should be the same in this. Here we should put R equivalent. So we can equate right sides of these two equations, so this part and this part, and that gives us that R equivalent is equal to R1 plus R2, or depends how many more resistors we have connected in series, would be Rn. So that is the rule for calculated equivalent resistance of two or more resistors connected in series. So next circuit which we want to consider is parallel connection of resistors. So we have such a circuit with some battery. Here we have one resistor, and here is one more. So let's consider that this battery provides potential difference at terminals delta V. So here we have say R1 delta V1, R2 delta V2. Since we have parallel connection, here we have also kind of split of total current flowing through the battery to two components. We have component I1 and component I2. So based on this circuit, we can write the following. First of all, total current is equal to the sum of two currents, and in the case of parallel connection, we have the same potential difference for each element of the circuit. So delta V1 is equal to delta V2, and everything is equal to delta V. So in this case, we also want to find some equivalent resistor, which will substitute these two resistors connected in parallel. So it will be R equivalent delta V, and here is delta V plus minus. So if we have equivalent resistor, means that the current here should be the same as in the first circuit. So how we can define this current? This current will be equal to potential difference, delta V, divided by resistance, R equivalent. And this current should be equal to the sum of two currents I1 and I2 in the first circuit. So means here should be delta V1 divided by R1 plus delta V2 divided by R2. Assuming that delta V1 is equal to delta V2, we can write here delta V as a sum of 1 over R1 plus 1 over R2. So eventually we cancel out this delta V and can write the equation for calculating equivalent resistor of resistors connected in parallel. So it will be 1 over R equivalent equal to 1 over R1 plus 1 over R2. If we have more, then also plus 1 over Rn. So here we have two rules how we actually show that these equations, how we derive them based on the general assumption about electrical circuits which we consider with resistors connected in series and resistors connected in parallel. So there is a difference between calculating equivalent resistor for series and parallel connection. This should be taken into account. And also don't mess it up with rules for calculating equivalent capacitance, because they are actually look similar but opposite. So we discussed in details this previously. I just remind you that it should not confuse you. So you need to distinguish clearly between capacitors and resistors in terms of calculating their equivalent values when you deal with some electrical circuits. So now we want to introduce two Kirchhoff's laws and consider some example how we can apply them to make our life easier when we deal with some electric circuits, not necessarily DC. It also applies for AC, alternating current circuits, but so far we don't deal with them. It will be later. So first, Kirchhoff's rule is so-called junction rule, and it states that if we have a junction, like connection of several wires, let us go here. For instance, we have one wire which goes into. So here is I1 current. Then we have I2 and I3. So this is for first current, second current, and third current direction. If we have such a situation, then the sum of all currents which go in and go out should be equal to 0, assuming that those currents which go into the junction, so this is our junction, those currents which go inside the junction, they are considered as positive, and those which go out considered as negative. So eventually we can write that I1 minus I2 minus I3 is equal to 0. So that is actually, in general form, we can write that the sum via junction for all currents should be equal to 0. So that is the first rule. It comes from the fact that we do not get and lose, like don't get any charges from nowhere. So we have the fixed number of charges which come to the junction. The same number of charges means per second per unit time when we deal with current should leave the junction. Eventually, the net balance gives us 0. So the second rule is so-called loop rule, and it is based on the following statement. So the sum of the potential difference, like let's say directional sum of potential differences across all elements around any closed circuit loop should be equal to 0. So we can write that sum over a closed loop for any electric circuit potential difference should be sum of all potential differences should be equal to 0. So that actually comes from the conservation of energy, because if we have some battery, for instance, it provides some potential difference to the circuit. It increases energy of electric charges. Then they flow through a closed loop, and when they come back to initial point, back to battery, this provided, since we are talking about steady state condition, so this provided external energy because of potential difference at the terminals of the battery should be dissipated on these resistors components or other components of electric elements of electric circuit, and eventually the total like net potential difference for any closed loop should be equal to 0, because that comes from the principles of conservation of energy. So how does it work actually? And yeah, we can also write that like this second Kirchhoff's law, loops law, as a sum of all products of electric current to resistors. For instance, if we are talking only about electric circuit with resistors, so each resistor, so kind of potential drops over resistors, should be equal to the sum of all electromotive forces which are embedded into this closed loop of electric circuit. So there are different ways how we can explain this loop law. So let us consider a possible application of this Kirchhoff's laws, how they can help us to deal with different electric circuits. So let us consider such electric circuit where we have two batteries. So it will be epsilon 1, epsilon 2, and several resistors. So we will have no, we need one more resistor here. Here, and then in diagonal, we have one more resistor. Okay, so that's our electric circuit. We have two power supplies. Then we have resistor R1, R2, R3. We can name some points of this circuit, let's say A, B, C, and D. And then we actually don't know because we want to get it in general solution, so we don't know the magnitudes even of this electromotive force, I1 or 2. We don't really know how electric current will flow because it depends on the ratio. However, we actually don't need to know this. We can just make some assumption. Let's say we believe that current is flowing like this. and here will be I1, I2, and I3. So that we define as direction of current. Later, if we were wrong, we will get just sign minus, so we can always figure this out. So it doesn't matter. And also what we want, we need to consider certain loops, which will be like closed loops and will contain at least one of new element. So that's the rule how we can apply. If we want to build in one electric circuit several loops, we want to be sure that in every second, like next loop, we get at least one new element. So let us consider two loops, which will be A, B, C, D. So that's first loop A, B, C, D, and one more loop, which will be A, C, D, A, C, D. So for first loop, the direction of the loop, we will choose clockwise. So that's for A, B, C, D. That will be our direction of the loop. Direction of the loop is important because that will define which of the potential differences will be considered as positive and which negative. And also for ACD loop, let us consider this direction of loop counterclockwise. So once we define these conditions, we can see how we can implement this, like apply this Kirchhoff's rules. So first of all, let us consider this junction C. Here we have two currents which are kind of going into this junction and one current going out. So based on this junction rule, we can write that I1 is equal to I2 plus I3. Then if we consider loop ABCD, taking into account that our path is chosen path is clockwise direction, we see, okay, so here we have plus minus and plus minus. So this direction of current generated by first battery E1 is in the direction of the path of the loop, so it goes as positive sign. Is electromotive force, and for other battery, the current which generates by this battery is in opposite direction to the path of the loop ABCD, so it comes with negative sign. So that is our left side of the equation with electromotive forces, and also we need potential differences in potential drops over resistors. So which resistors we have in this loop? We have resistor R3 and R2. In case of resistor R3, the electric current coincide in direction with the path of the loop. So then we could take it with a positive sign. So it will be I3 times R3. And here we see that the direction of current through resistor R2 goes in the opposite direction to the path direction of the loop. In this case, we take this with sign minus, I2 times R2. So that is equation for loop ABCD. Let us consider second loop, which is ACD. So in this case, we have positive electromotive force of battery 2, E2, and also here on the right side, we have positive potential drops for resistors over resistors R2 and R1, since electric current I2 and I1 flow in the direction of the loop path. So here we have I2 times R2 plus I1 times R1. So once we define with this electric loops and equations associated with them, we can write a set of equations. So here we get epsilon 1 minus epsilon 2 is equal to I3 times R3 minus I2 times R2. And second one will be epsilon 2 is equal to I2 times R2 plus I1 times R1. And the third equation, which is necessary here, is also the equation which we got from the junction law. So we can write that I1 is equal to I2 plus I3. So if all parameters of the components of this electric circuit are given, then we can calculate this electric circuit, these electric currents. So we can consider I1 as some unknown X, I2 unknown Y, I3 unknown Z. And by solving this linear set, like system of linear equation, we can get the values for all unknown electric currents in the circuit. So that is an example for application of this Kirchhoff's rules when we deal with DC circuits. And I see we still have some time, that's good. We can also discuss this important topic with RC circuit, since quite possible you will have some problem for midterm also including this topic. So RC circuits. As I mentioned at the beginning, we so far deal only with electric current, which is constant in direction and constant in time, in magnitude over time. So that not only is a possible option for direct current. Direct current means by definition current which does not change the direction. However, it doesn't state that it should not change its magnitude over time. So that's what exactly happens when we have RC circuit. So let us consider such electric circuit. We have some battery. We have a switch here, let's say. Then we have a capacitor. Then we have a resistor. So what will be the current in this circuit if I switch on this, like turn on this switch? Any ideas and suggestions? What will happen here? You remember?
Will be charged up.
Yeah, capacitor will be charging, means that we will have some current flowing through this circuit. But you remember that capacitor is just a capacitor is just two plates with some insulator between them. So if we have insulator between these two plates, it actually means it's open circuit. So there is nothing there. And the question is, how can current flow through this circuit if it's just open? It's like equivalent to this switch. If it's open switch, capacitor could be considered also as an open switch for electric current to pass through. However, it takes some time to charge this capacitor. So it should get some positive and negative charge on its place. And in order to charge capacitor, we need to transport charge in the circuit, means there should be some electric current. It will be DC current because it will be in one direction. However, obviously this magnitude of this current will depend on time. So initially, when we have let's say t equals to 0, then we can say that this current will be maximum because there will be no potential drop over capacitor. It will be discharged at t equals 0. And then maximum current will be equal to this electromotive force divided by resistor, assuming that we don't have some ideal battery without internal resistor. However, over time, when electric capacitor will be charged, there will be some gained potential difference at the plates, and that will cause reduction in the electric current. So according to Loop's rule for this second Kirchhoff's law, we can write for this electric circuit that we have epsilon, like electromotive force, minus Q divided by C, which is potential difference at the plates of the capacitor, and minus I times R. So that should be equal to 0. So they will, this potential difference generated by battery will be kind of split between two components, which is potential drop over capacitor and resistor. So if we increase potential drop over capacitor, then means that will be reduction in potential drop over resistor, and obviously electric current will start to decline. So the maximum electric charge which can be accumulated by this resistor, Q, is equal to capacitance of this resistor times electromotive force of the battery. So this process of transient process of time-dependent current flow through the circuit will continue until from t equals 0 when we turn it on and we have maximum current I equal epsilon divided by R. And it will continue at t approaches infinity in general case when we fully charge this capacitor. However, obviously, the time which will be required to charge capacitor will be determined by capacitance, resistor, and electromotive force. So in order to understand how all these processes and parameters in the scope of this process of charging capacitor will be related with each other, we need to write a differential equation and solve it. So how we can write the expression for electric current? In general, we can write the following. Electric current will be equal to so it actually comes from this equation, which we wrote based on the loops rule. So electric current, if we rearrange it and express electric current, it will be epsilon divided by R minus Q divided by R times C capacitance. So that is expression for electric current, but it doesn't tell us the time dependence of this current. So it just gives us the magnitude of electric current at a moment of time when electric capacitor, this capacitor, accumulated electric charge Q, but we don't know how it changes with time. So in order to know this, how it changes with time, instead of I, we can put its relationship to the rate of charge change. So we can represent electric current as first derivative of electric charge over time. And now we have a differential resistance, which provides information on time dependence of electric charge Q accumulated at the capacitor. So this is the first step, and we need to solve this equation in order to get time dependence of electric charge accumulated in capacitors in this electric circuit. And then in order to, when we have this Q as a function of time, we can take first derivative over time of this function and get expression for the time dependence of electric current in this circuit. So first, let us rearrange a bit this. Let us multiply and divide first term of this equation by C. So it will be epsilon C divided by RC minus Q times RC. And now we can set it to the common denominator, would be written as minus Q minus epsilon C, and this is divided by RC. So now we can rearrange the variables so that dq and q will be in the one side and dt will be in another. So it will be dq over q minus c epsilon, and it is equal to minus dt over RC. So that is our final form for differential equation, which we will now integrate left and right side and get the function q as a function of t. So let us write down this equation on the next slide. So it is dq over q minus c epsilon is equal to minus 1 over RC times dt. Okay, so we integrated because this is constant, R and C, they are constant, so it's not necessary to put it under the integral. So here, what we need to do, we need to subtract C times epsilon from Q in order to have under the differential the same expression as in the numerator. So we can apply tabulated like integral. And now we can integrate this. So it will be natural logarithm of q minus c e, like c times epsilon. And that is equal to minus t divided by r times c plus some constant. So we need to define this constant in order to get the final expression for the equation we are looking for. So what we can consider, we know that at t equals 0, our capacitor is not charged, so means q equals 0, 2. So now let us substitute these conditions in the equation here. So it will be natural logarithm. Q is equal to 0, so it will be just minus c times epsilon. And t is equal to 0, so it will be just this constant c. Maybe let us write this constant somehow differently, maybe a, because we can be confused with capacitance c. So it will be constant a. So then we see what will be equal our constant. It's natural logarithm minus c times epsilon. Now we can substitute this in the equation in order to get the final function. So it will be natural logarithm of q minus c epsilon. Then we have this constant a. Instead of it, we put natural logarithm that we can do like this, minus natural logarithm minus c epsilon. And that will be equal to minus t over rc. Taking into account features of logarithms, we can write that this is natural logarithm of q minus c times epsilon divided by minus c epsilon, and it is equal to minus t r c. Okay, so now we want to express u as a function of time. So for that purpose, we need to take the left and right side to the exponent to get rid of the natural logarithm. So that will be q minus c epsilon divided by minus c epsilon. It is equal to exponent of minus t divided by rc. And now we can express the like q as a function of time. So here we can write q as a function of time. It is equal to c times epsilon minus c times epsilon times exponent minus t over rc. Keep in mind that c times epsilon, that is the maximum charge which can be accumulated at the capacitor, and that is equal to capacitance times electromotive force. So instead of c times epsilon, we can put q, capital Q, and take it out of parentheses. So we will get capital Q times 1 minus exponent minus T over RC. So this is the time dependence of electric charge accumulated at the capacitor. And we'll see that it actually goes from, if we have now if we want to proceed further and calculate the electric current as a function of time, what we need to do, we need to take the derivative of this expression. So let us write it down on the next slide. So it was Q as a function of time is equal to capital Q 1 minus exponent minus T over RC, and electric current as a function of time is equal to first derivative of this function, which we derived previously, over time. So if we take this derivative, it will be equal. So let us, for taking this derivative, let us write this with epsilon times C, because it will be more convenient for us. So let us write here like C times epsilon. We can do both. Oh, sorry. With taking derivative, we will get, so we open the parentheses and take derivative. So let us open the parentheses. So it will be minus C epsilon times exponent minus T over RC. And here we need to multiply by derivative also of argument of exponent, which will be just minus 1 over RC. So now we can cancel out this capacitance in the numerator and denominator, also cancel out these signs like minuses. So it will be eventually epsilon divided by R. So this maximum current, which could flow through the circuit at first moment of time when we turn on the switch, times exponent minus T over RC. So we see that with time, electric current through the circuit exponentially decreases. If we analyze time dependence of electric charge and current, electric charge accumulated at capacitor and current in the electric circuit, we will see something like this. So here is time, here is electric charge, and charge on the capacitor will increase like this, approaching this maximum value C times epsilon, which is equal to maximum charge Q. And if we consider electric current as a function of time, that will be exponentially decaying function. So it will go from maximum value at I naught equals to epsilon over R, and it will approach 0 over time, while electric charge accumulated at the plates of the capacitor will approach magnitude C times epsilon. So these are time-dependent characteristics of charge accumulation and electric current flow through RC circuit in the charging mode. You can also later check by yourselves what will happen if we have already charged capacitor and it will discharge via resistor. So how electric charge and current will change in that case. But overall principles are very similar and it will be easier to understand. So, okay, with this, I would like to finish our discussion. If you have questions, you're welcome. Keep in mind that on Saturday, our first midterm is coming, so please take your time and revise all material. Always check the manual for all topics which will be covered by midterm, and just prepare for this. So be aware that on Saturday we will send invitation a bit later this week, but just as a reminder, would like to highlight this. So today we discussed connection of resistors in series and parallel, figure out how to calculate equivalent resistors for such circuits, considered first and second Kirchhoff's rules, and also introduced so-called RC circuit when we have DC current, which is time dependent, so which is changing over time, and derived time dependence of electric charge accumulating on a capacitor connected in series to resistor and battery, and also derived equation for time dependence of electric current which flows in such electric circuit. Electric current starts from maximum value and exponentially decays, and electric charge at the capacitor goes from 0 because we have uncharged capacitor, and increases up to like approaching to the maximum value, which is defined by the product of capacitor capacitance of this capacitor and electromotive force of the battery. Keep in mind that in this exponential function which we derive, there is exponent minus t over RC. This RC product is actually a time characteristic of this RC circuit, and it defines its magnitude, defines how fast we can charge the capacitor. So we want to have small capacitor and small resistor in order to charge this capacitor fast, because there will be smaller amount of charge needed to fully charge this capacitor. And if we have smaller resistor, obviously it will result in larger current. So larger current means we will accumulate more charge per unit time. So if we keep, for instance, capacitance constant and increase resistance, obviously it will result in reduction, like increase of the time we need to fully charge this capacitor. So that's why, based on the product of C and R, it's some so-called time constant, tau, of this RC circuit, we can see how fast eventually this capacitor will be charged, and electric current will stop flowing through such circuit. Okay, thank you very much for attention. Prepare for midterm, take care, and see you on our next lecture.
Thank you. Thank you.
Bye-bye.